Good evening. Today we will discussing about remote sensing and GIS applications in urban and regional planning. So you see, in urban areas, most of our databases are in the conventional manner. Either they are kept in a file format or hard copy map. So if we want to extract some information from that and retrieval of some evidence data set is required on an urgent basis, then it is quite a tedious process, and it takes lot of time and resource also. And that is why, since urban areas they are a very dynamic in nature, so there is a urgent need basically to have databases which can be accessed very fast and are also dynamic in nature. So here is where remote sensing and GIS comes into planning. Remote sensing basically serves as a spatial data provider. It provides you spatial data which is very accurate and up to date. While GIS provides you an environment where you can handle this data. Basically, you can generate data, spatial data from a number of data sources. You can integrate the data and analyze the data, and subsequently you can also transfer the data to other people very fast. So as I told you, urban planning is a very dynamic field. So here we require databases which are urgent and which are updated at a very less temporal resolutions, because urban growth is urban areas are very fast and changing in nature. So if you go by conventional field survey methods, then collection of those spatial data takes lot of time. It is not impossible, but it takes lot of time. So if we have to generate a master plan, then we require this spatial data, accurate and updated spatial data. So normally that is not available, and then sometimes the planners they have to manage with the old databases. Okay, so here is where remote sensing comes into play. It provides you spatial data which is very accurate and updated also. And secondly, as I told earlier, geographical information system, or we will use the word short form, that is GIS. It basically provides you an environment where you can integrate this data coming from remote sensing along with the socio-economic data that is coming from the ground, and using this digital database you can go for analysis type of, you can go for analysis also. Okay, especially if you have to develop a master plan or a development redevelopment plan of a small area in urban, then you can use this GIS and it will be very helpful. And if you see, under Amrut 1 and Amrut 2, there is now more and more emphasis there on a GIS based master plan approach. So in this also we are using remote sensing data as the input data, and GIS is being used as a handler of this. So broadly, if you can say, remote sensing is a spatial data provider and GIS is a spatial data handler. These are broadly the role of remote sensing and GIS in urban planning. Now, just to explain what we have discussed in the previous slide, remote sensing images are like this. Okay, this is the built up urban area. These are the surrounding green areas or agriculture areas. These are the agriculture areas, these are the forest areas, and this is a river which flows through the urban area. Now this data is, if you collect from ground, it will take lot of time, but from remote sensing it provides you a synaptic view at a large scale, and So this is what remote sensing does. It's basically a spatial spatial data provider. While you see in a GIS, you can, using this remote sensing images as source, you can generate a map. So this is basically a map generated, digital map, which is generated in a GIS environment using remote sensing as one of the inputs. And later if you want, you can also attach attributes like this parcel or this building, whether it is commercial, it is industrial, or it is residential, these, or who is the owner of this parcel of land or building, height of the building, building construction materials, age of the structures, these kind of socioeconomic data, we can say ground data, you can integrate along with the map in a GIS. So again, GIS is more of a spatial data handler which integrates data which is coming from multiple sources, from remote sensing and from ground also. So as I told you earlier, this is a map which is created in a GIS. Now this data which we call as the attribute data, it basically tells us like this is the ground data which we collect and attach it with the mm, map generated in a GIS, like what is the age of the building, when it was constructed, what is the number of floors, what is the material, and whether it has been affected by flooding, and what is the probability of flooding, very low or high. These kind of data sets we can integrate. And if we want, we can integrate other data sets, like if this is a piece of land, parcel of land, I showed you where is the location, which village or which area this thing is falling, what is the other details of that area, who is the owner of the land, and what is the address, and all the revenue records, the khasra number, and which we have, which you call as the revenue records. This kind of information can be added to this GIS based map in a GIS. Okay. So now you see this is a photograph. Now we are telling now what, why we require different resolution data sets in the remote sensing. You see, when we acquire images, if you are acquiring your images also, or when you buy a phone, uh, the seller tells you like what is the pixel or what is the resolution of this, what is the DPI, he tells you. So that means what is the, you see, when we take a image by satellite imagery or by your phone and digital camera, it acquires the images in this kind of grids. Okay, and each grid contains information about the whole scene. So you see this grid, if you see, it will collect information like this is a house, but this is this, and this is this. But you see in some grids you will have mixed information. Partly the grid will be cell, you can say the cell will be lying in built up area, and part of the cell will be occupied by the you see here, it is a part of cell is occupied by built up house, and part is occupied by this agricultural land also. If you see this also, you see this area is built up, building part of building is coming here, also building is coming, but part of the cell is also occupied by the agriculture field, or some kind of agriculture is happening place. So you see, when you make a image, your details will be lost, because this will be more of what is called as a mixed pixel. Okay, if you take even a coarser grid or a lower DPI, then you see what will happen in this house, and this entire green area will, and this mountains also, hill ring also will be falling in one grid. So that means here you cannot make out which, whether this house or this is agriculture field, or this is a part of sky, or this is basically a mountain. So this is more of a pixel, it is called as a mixed pixel. So if you take more coarse resolution grids like this, your informational detail will be less. But if you take finer grids like this, you will get better information. But the disadvantage is, if you take small grids, if you take further small grid, you can say you will get more information from the picture, you can delineate more features. But the problem is, if you make this grid size small, the volume of the image will be very large. So you require larger storage image and better processing facilities to process this image. But if you take this image, here you see, although the details will be less, but the size of the image will be less. So storage space required will be less, and processing power required will also be less. So this is called as a fine spatial resolution, and this is called as a coarser spatial resolution. Okay, and this is a basically a fine spatial resolution. So same thing we are converting to image also. This is an image which is acquired at 23.5 meter spatial resolution. So if you see this image, you can make out small details from this. Okay. This is river, this is built up, this is again river. Why we are recognizing river? Because it is meandering in shape. But you may say the color is cyan both in river and the built up, because this is a dry river, so most part of it is basically occupied by boulders. That's why their signature is matching with that of the urban areas. Okay. But if you see, this is the image where the grid size is 23.5. But here in same area, we have taken the image at resolution of 5.8. Same as exit, this is 23.5. If you consider 23.5, this may be what is called a 5.8. So if you see, compared to this, you can make out more detail, because here there will be less mixed pixels. You may get some pure pixels. So you see, your information content has suddenly increased when you go from coarser to finer resolution image. So you can make out this. See, you can make out a playground. This is basically parade ground. You can make out agriculture areas. Even built up, you can find out which is more dense, which is less dense. You can make out the railway line, some roads also. Okay, and you see this. Here also details are more. You can make out the buildings. This is basically the approach road. This is the area around the building. So you see, as the pixel size has decreased, or the spatial resolution has decreased, suddenly your information content has also increased. But this requires less storage space. The image is of less size, and here it requires more space, and of course it requires more of processing power also, right? Now this is 23.5, this is 5.8, and this is 1 meter. So if you see, as we are going from 23.5 to 5.8, and then we are going to 1 meter. The moment we approach 1 meter, you can see a number of things. You can see this, you can see the roads, you can even see the vehicles moving on the roads. This is a park, you can see the fountain, you can even see like this is the area at 5.8. Here it is not visible that much, and 1 meter you can even say this is a ground, and here we have got some public function going on. So kind of there we have buses, water tank, a pathway, roads. You see, this is the same area, this the building, these are these things. But when we come back, you see, suddenly you can even see this cricket pitch also. If you see very clearly, you see these are three buildings, here. Here this not very less available, but if you go here, suddenly you can even see like this is a park with trees, this is a fountain, there is a road here, tree lines are there, this is a cricket ground, and this is a public ground which is used for various public functions. So you see, this is the effect of resolution. As we use high resolution images in urban planning, we can extract more and more of information from the image. But the only thing is, higher spatial resolution means more cost of the image, more storage space, and more processing power you need to handle and analyze these kind of high resolution images. Okay, this is another image. You see here exactly, you can see this is built up. Okay, these are the roads, the water bodies. So this is again part of that image. But one thing is, Suppose you want to delineate something. So what you can do on a computer, you can manually digitize. This is the road. This is the outline outline of the structures. But generating a map manually will take a lot of time. So what we are doing now, we are using various algorithms, machine learning based or normal mathematical algorithms we are using, and using these algorithms, you see, we can sometimes delineate the objects automatically. See, what I meant to emphasize is, if this is a high resolution image and you want to generate a map of this area, you see this is appears to be a water body, you can say, with some water. This is just a bare field, it's a vacant field, and these are the houses, these are the roads, okay, and different kind of structures here. And what you see in red color, because this is a standard FCC, so what you see in red color is basically vegetation. Basically it is a tree cover, you see. So sometimes you want to make a map out of that. One of simplest ways, you open this image on the screen, and in a GIS, one by one, manually you can go about delineating the each structure, dilating the outline of the vegetated areas and water body. But it will take a lot of time, you see, because city is quite big. So what we do is, we have now developed various algorithms where automatically, by giving some input parameters, you can delineate the objects, you see. So you can delineate these objects. This is the built up row housing, okay, this is the vegetation. So if we can automatically generate objects from the image, then our task will be quite simplified, and we can generate a base map of a city from high resolution satellite at a very fast, in very fast, in very less time we can generate the map, okay. So first thing we are going to do is how we can extract building footprint extraction using different algorithms. See, this is image of area, you see this is in 2018, this is 19. So what we are doing, we are having a redevelopment of this area, yes. So what we have seen is 2018 image, then in 19 this much area was cleared, and slowly you can monitor, you see this is the 2020 image. So what we have done is, see, manually digitizing this buildings will be a very tedious project. So what we have done is, using various machine learning algorithms, we have generated a 2018 building map, this is 2019 map, and this is a 2020 map. So this shows you, like, these are the buildings, this is how the work progressed, and now this is what final has done. So this all thing we have not done manually, we have done using an algorithm. So what I want to say, for delineating extraction of building footprint, now we are using basically various machine learning algorithms by which we can generate the map at a very fast rate, okay. So this is basically a standard FCC, okay. Second thing is, now in a city, you see, we want to find out, like, what is the building footprint map, what is the road, and what you see in red is the center line of the road. So if we can generate these maps knowing the partial boundary, parcel, or the building footprint maps, then these kind of maps are very useful basically for the municipalities or for the urban planning authorities. These kind of maps are very useful. They can be used for taxation purpose, for urban cadastral purpose, and if you want to provide social infrastructure facilities in a particular area, then these kind of maps are very much required, especially by the urban local bodies, maybe the municipalities or the municipal corporation. So you see, using remote sensing, we have tried to generate a map showing the urban building foot map. So if we can overlay time these maps of time T1 and in T2, we can also say how the urban growth has taken place, which buildings have now come up in the past few years, and where they have come up, okay. So this is how using remote sensing we can generate large scale map footprint maps for urban areas, which can be used for urban taxation, urban cadastral, and other urban planning process, or for development of various generation of various development schemes also. Okay. So this is for one ward of Dehradun city. We have generated a map which shows you the, these are what you see in yellow are the buildings, these are the parcel boundaries, and what you see in red, these are the road network. Okay, so this is a map which we can generate very fast, and we can generate this map for different time periods also, and use it for monitoring of urban growth and for another various urban administration purpose also. Okay, so if you either you go for a machine learning algorithm, if you don't go for a machine learning algorithm, then what you can do is you can also do a visual interpretation if you are not having access to any kind of technologies. So what are the elements by we can interpret is, the first thing we can do is the size. Okay, based on the size we can delineate an object. You see a car has got a fixed size, a bus, a truck has got a fixed size. Similarly, we can delineate the building based on the size also. A factory will have a very large size compared to a residential building. The shadow, the shadow gives you idea like what is the height of the building. Okay, the shape, you see a stadium will have a very peculiar shape, so you can identify some features based on the shape only. It may be a cricket stadium or a football stadium, so it will be a oval shaped. Okay, and some factories or large structures also you can identify. Second is the pattern. If the buildings are arranged regularly or they are not arranged regularly, that can also help us in identifying some objects. And last is the tone. Tone means the color. You see these buildings, they have got a yellow color, and what you see in this is basically the bare soil. So based on color and association, you see association means if there is a building and there is a chimney near it, then you can easily say this appears to be a factory. Or this is a building and you've got a number of playgrounds, you may say it's an educational institute. So basically using these elements of shape, pattern, means how the buildings are arranged, the texture, the size, the shadow, tone or the color, and the association between the various elements which are placed like a chimney and a building, you can say this appears to be a factory. So we call it as the association basically. So based on this association, you can basically visually also, without, see, suppose you say I am not having to any kind access to any kind of algorithms, or I am not familiar with any kind of algorithm, then the simplest thing is you can basically interpret the image manually uh, based on this which I told you, this 1 2 3 4 5 6 7 elements of image interpretation. So sometimes if you are asked, then these are the 7 elements of image interpretation. Okay, by which you can visually also interpret a high resolution or any resolution image you can interpret. Okay, now what we have done is, after we have created a footprint map, then we have gone to the ground and we have tried to find out what are the activities that are taking place in each parcel of land which is being used for residential purpose or commercial or school or religious, or basically it is a combination of both residential and commercial. So if you see here, you can see in yellow color these are the residential buildings. In red color they are mixture, we are having a mixture of both, a mixed land use we are having, so that is residential and commercial also. These are the purely commercial buildings, these are the educational buildings, and these are the religious buildings which you are having. So you see, we first, using remote sensing, we first generated a footprint map, a map showing the outline of the buildings and the boundaries of the plots on which buildings are located. Then we generated a road map showing the major and the minor road. So these roads were classified based on the width, which is arterial road, sub-arterial road, and finally we went to the ground, and for each building we associated a land use. Land use means the activity that is going on in each building, human activity, residential, commercial, whatever is there. So now what we have got is, we have got what is called as a land use map of a particular ward in Dehradun city. So you see, we are just doing all the exercise in remote sensing. Remote sensing first is gave out the data. Based on, we took the data in a GIS environment, and then in a GIS environment we created a building footprint map, and then which this building footprint map, based on ground data, we have found out what is the activity going on in each piece of, in each building. Okay. Then we have also tried to find out, you see, now you see, what we are doing is, after generating a base map or a footprint map, we have started associating the various attributes with each building. So the first attribute which we associate was, what is the land use. The second thing is we have done is, what are the income group. So what we are finding is, like, there is a clear segregation between the income group. While the higher income group, they tend to aggregate here, the middle income group, they tend to aggregate here, the low income group and the economical weak group, they tend to aggregate here. So you see, what we done is, if we take this information in a register format, which I told you in my first slide, that's how we are recording the data. Like, in a register format, or if having in a tabular format Excel sheet, then you cannot visualize how the data is distributed on the ground, or what is the clustering of these data sets. Okay, what is the clustering of these data sets on the ground. But now what we have done is, we have mapped this data. So using GIS we have mapped the data, and now easily you can find out what is the spatial distribution of the data, whether different income groups, they are dispersed randomly, or whether they turn to follow a particular aggregation. So what we are seeing is, people with a particular income group, they tend to aggregate together. So this kind of spatial analysis, you see, you cannot do if you have got a tabular data or data in an Excel sheet, as we discussed in the first slide. If you have got a tabular data sets, then you cannot do this kind of analysis. But if you have generated a map, and then a GIS, you have attached that all data to the map, then spatially you can see how the variation of various variables is taking place. So this kind of analysis is very important if you are going for urban planning. Suppose you want to provide a some common facilities for the economic weaker section, then we know this is the areas where we have to target. So if you want to do some kind of development plan, or you want to provide some kind of infrastructure facilities, then it provides you a rational ground on the basis of which you can take this kind of decisions. Okay, then we have done one more analysis, where we have found out, like, where the income group and the type of settlements, what is the correlation between them. So what you find out, like, in brown color they have the formal settlement, and yellow color we have the informal settlement. So formal settlements are settlements which have proper approval of the development authorities or the city authorities, whichever is the regulating authorities. While informal settlements are those where we don't have much of, maps are not approved. Okay, where maps are not approved, and they are type of a disorganized type of settlements have taken place. So what we are finding out is, like, you see, most of the higher income groups, middle income groups, they are following in properly planned areas, you see, and while most of the economical weaker sections, they are going in the informal settlement. So if you see formal settlements, they have got a well layout road network, arterial road, sub-arterial road, inner roads. So they have got a very good layout, and you have got a very proper structure you can provide. Infrastructure facilities are there. But if you see the informal settlements, where basically we have the EWS sections deciding, you see, the development is taken place in a very haphazard manner. We don't have much of a planned layout, you see. So these things, if you see, they are very clear on the imagery also, you see. I don't have the imagery of that area, but if you see the imagery, sometimes by seeing the imagery also, you can say this area appears to be a well planned area, while this appears to be a not planned area, or it may be a informal settlements. So you see, from remote single image we can extract a number of information. We can even try to find out what is the building densities, whether this road network is planned or it is unplanned, whether the layout is proper, or it is just organic type of growth that has taken place. So for a single image, you see, you can find out the building sizes, the type of layout of the areas, the road network, and you can see, you can even infer which appears to be a planned area and which appears to be an informal area. And you can also try to make a guess like what could be the segregation of the people, demographic segregation based on the population, on the income also. So you see, from a single image in urban planning, we can extract a lot of information, and this information can be very useful when we are generating a master plan of this area. You see, when we develop with after normally within we generate a master plan. So a master plan, we have to basically, it provides, a master plan provides a document for future growth of the city. It is a vision for future growth of the city. So uh, we need a proper assessment of what are the conditions on the ground. So for taking future decisions, they provide a rational basis for taking future decisions. So for master plan generation, which guides the future development of a city, we require this kind of data sets. And using remote sensing, a number of, I will just see a number of inputs can be generated, which can be very useful for the planning purpose only, for the development plan or master plan, or if you have got a redevelopment plan for a small area, it can be very useful. Now third thing is, suppose we want to redevelop a area, then we want to find out, suppose we widen a road by to 13 feet, then we want to find out how many structures will be affected by this widening process and how much compensation we have to provide. So you see, this tells basically, if you go for a right, this, what to see this color, okay, this is the color. If we say we widen these roads by 13 to 13 feet, then the buildings which are highlighted in this color, yeah, this, okay, these buildings will be affected. These buildings will be affected if we carry out a widening of a road in particular area. So this gives an idea like what will be the population that will be affected, what kind of rehabilitation work we have to do, and how much we have to pay compensation also, because that's also important part when we have to implement a scheme on the ground. So you see, a single image, you are deriving a number of inputs which are very crucial when we go for future planning of the urban areas. Okay. Now you see, uh, this is basically Dehradun, part of Dehradun city. So what we have done is, what you see in red basically are the vegetation, this is the built up, and this is the road. So you, as I told you earlier, first we generated a map showing the building footprint or the plot boundaries. Then we went to the field and tried to find out what are the activities that are taking place in each plot, where the schools are located, where we have the open areas, where there is administrative, commercial, education, medical, office, religious, residential buildings, and buildings having a mix of residential and commercial building. So you will see that most of the buildings here, they are basically residential buildings, while buildings which are located along the roads, they have got a mixture of both residential and commercial. And inside we have got a lot of open spaces, as they are basically orchards in this area, and plus we have got some offices also. So you see, using a high resolution remote sensing image in a GIS environment, we have generated a map which shows you the updated and the current activities that are going on in that area, and the building footprint map, the buildings, outline of the buildings and outline of the plots on which buildings are located. So this is how we have generated a land use map using a remote sensing imagery, and this is one of the most crucial inputs we require for any urban planning exercise, because urban planning is basically a spatial process. It's a spatial process we do, so we require up to date spatial data sets. Then once we have generated these footprint maps, then we have gone to the ground, and by field survey we have attached information to each building, whether which building is framed or which one is load bearing. Framed means we have got a pillars which are columns which are supporting the buildings, and load bearings were basically built earlier where the load was taken by the walls and we were not having those framed structures. Okay. Second thing, attribute data which we have collected is what are the buildings which are having a RCC roof or a reinforced brick concrete roof. And third, what we have done is we have collected data like what age of the building, basically which building is old, which is moderate, and which is new. So the basic thing we have done is using remote sensing image we have created a base map, and then by field survey in a GIS environment to each building we have added some attributes like what is the building structure type, what is the roof material type, and lastly what is the age of the building. Okay. Fourth is what is the proximity between the buildings. See why we are doing it, this exercise is we wanted to find out in this particular area what will happen if a earthquake of a particular strength comes, because as Dehradun is located in a very much seismic prone area. So see what happens when an earthquake comes, these buildings will collide with each other, and because of this hammering effect destruction will occur to both buildings. So here we have tried to map what is the difference gap between the building, okay, whether it is less than 1 point, the gap between the adjacent buildings, is it less than 1.5, is it 1.5 to 3 meters, or it is 3 to 6 meters, because we want to find out how many buildings will be affected by this hammering effect that happens when the two buildings collide with each other during a earthquake. This data we have collected is what is the number of floors. So what we found out was inside most of the buildings were ground floor, but along the road if you see buildings were having a mixed land use, commercial also and a residential also. So here we tend to have a ground plus first floor. So most of the buildings here were ground or ground plus first floor. So you see what we are trying to do is using remote sensing as a spatial data provider, we have generated a footprint map, and then in a GIS environment for each building map we are generating layers by attaching various information to these layers like the type of buildings, the age of the buildings, the distance between the buildings, the number of stories that each building has. Because when we generate the spatial database in a GIS environment, subsequently we will be using this database for analyzing what will happen if an earthquake of a particular strength occurs in our study area. So the methodology we follow is basically we generate a scenario earthquake. Using remote sensing and data, we generate a baseline data which I discussed. It is nothing more than a spatial database which we are using. And then in a GIS only, using this baseline data and the earthquake parameters, we try to estimate what will be the damage to the various building types. Okay. So here what we have done is we are trying to show what will happen. So we have generated a spatial database using remote sensing and GIS. Then in a GIS environment only, we have tried to analyze what will happen if an earthquake of 10 intensity occurs in a study area, or earthquake of intensity 11 occurs in our study area. So you see, say at an intensity of 10, these buildings will have a see the mouse is there, just a minute. Yeah, so you see these buildings in yellow, they will have a collapse, while other buildings will have a structure failure. But when the intensity of the earthquake, which is basically measured on a modified Mercalli intensity scale, you see a number of buildings will have a collapse, while some have a major structure failure. Now what we can do is, we already have a land use map, like here you see, we have already generated a land use map. If we overlay this destruction map on the land use map in a GIS environment, we come to know buildings which are having total collapse, what is the activity that is taking place inside this building. whether if it is a hospital or it's a school and that building will collapse, then either we need to take some structural measures to strengthen that buildings, or we may have to shift that school also, right? So you see what we have done is, in a GIS environment using remote sensing, we generated a database, we analyze that database, what will happen if this earthquake occurs, and then spatially we are trying to show which buildings will collapse, which will not collapse, and this we can overlay with the land use map and tell whether buildings which will collapse, what is the kind of activity going on, what is the kind of residential, commercial, what is there. So if it involves people which are having large population, then we may have to take some preventive measures also, or mitigation measures also. And we can also analyze whether buildings which are having total collapse, you see here buildings tend to cluster together. So this kind of spatial analysis we say why buildings which are having total collapse, they are having to cluster together. Are the building stock too old in this area? So if the building stock is old, then we can give a notice like these buildings may be demolished and we can come up with a new construction. So these kind of spatial analysis also we can say like why buildings which are having total collapse, they tend to cluster in an area, or are they dispersed. So this kind of analysis we can do very fast and easily and accurately in a GIS environment compared to the way earlier when we are storing or doing this analysis in a spatial format. So this kind of spatial analysis, which called as topological kind of things, we can do very fast in a GIS environment. Okay, see one thing which happens is when an earthquake occurs, we have got blocked roads. So once we have blocked roads, the major thing is neither we can provide rescue and relief operations. We cannot do any rescue and relief operations. So here what we have done is, using the remote sensing image, first we have tried to find out what is the width of the road, material of the road, and the road type, whether it is, you see, it is a bi-lane or it's a primary road. So this tells you what is the volume of the traffic that will be moving on this road. Second is the width of the road, of course, it's a 3 meter, 5 meter or 6 meter road. And lastly, what is the building material, whether it's a kacha road, pakka road, it's having asphalt or it's having a non-asphalt. Okay, so now what we have tried to do is, using this information and the damage maps, you see what we are doing is, we started from generating a spatial database, generated a base map, generated a spatial database by attaching information. Then we try to analyze what will happen in an earthquake, if how many buildings will collapse, how many buildings will not collapse. We correlated those buildings, what kind of land use is going on in their buildings, whether it's a what you call this a school is there or it is a commercial activity. So what we try to correlate is whether buildings which are having a total collapse, what kind of activity is going place. Thirdly, what we have done is, in case of a earthquake of particular strength, which buildings we have mapped will be blocked, or which have got a less probability of blockage. So you see this tells us this area which is a commercial area, this has a very high chance that this road may be blocked, as the nearby buildings may collapse and block this road. So if we have got a hospital here, that hospital will not be functional, because neither we cannot do anything, neither we can move in or neither we can move out anything. So this building, this hospital may not be able to function. So either we have to shift the hospital or we have to provide an alternative route. Here you see these sections of the roads may be blocked, but here these sections have got a relatively less probability of blockage. So this kind of analysis scenario can see if we can generate. So what we have done is, using remote sensing and GIS, what we have done is, first we have generated a base map, then we have tried to estimate what is the damage to the structures, what is the kind of land use that is going on in each structure, which road has a high probability of blockage, which road has a low probability of blockage. So all these things you see, they will provide excuse me, all these things, they will provide a very important input when you are trying to plan a future growth of the city, or you are trying to make a disaster rescue plan of the city, the disaster authorities also. So they require these kind of data inputs. So what we are using is, using remote sensing and GIS, we are generating various kinds of inputs that can serve very useful or that can provide a rational ground to the urban planning authorities for taking decisions regarding the existing network, existing infrastructure, and the proposed future growth. They can prioritize where it should be taken, where it should not be take place. Okay. One more thing we have tried to estimate is, like we have estimated how many buildings will collapse, how many buildings will have a major structural failure. So you see, so based on that we have tried to estimate. You see, if a earthquake occurs in a day, what will be the what will be the loss, or what will be the this fatalities we will have, okay, or or we can say injuries we will have, and what will happen if the population occurs during night. So we are also trying to estimate if in a particular area. So first what we have done is we have surveyed how many people are living in each building, and then we have tried to find out like which building will collapse or which building will have a major structural failure, and based on that we have tried to find out like how much is the population that is at risk during daytime or not time or night time. So you see, we are trying to estimate what how much population will be affected if an earthquake of particular intensity or strength occurs in our study area. Last thing is, you see, so till now we see, first we generate base maps and we try to generate a plot boundary, road structure, and try to do a socio-economic kind of study for a study area. Secondly, we try to estimate how many buildings will be damaged, how much population will be affected, how many roads will be blocked if a particular earthquake of a particular strength occurs in our area. Third thing which we have tried to do is we have tried to find out how the city has grown. So we have taken remote sensing and aerial photographs of different time periods, and then we have generated maps, and then in a GIS environment we have overlaid these maps. So this tells you how the city has grown temporally over a period of time, like we have done for 73 to 98. You can see how the city has grown, where it has grown, and then you can correlate what was the reason for this kind of growth pattern the city has shown. Was it because we had a new road, or basically the land cost was less in particular area, or there was better infrastructure facility in particular area, that is why the city has grown in a particular direction, or maybe there were some physical barriers in terms of maybe a mountain, or there may be a river, or there may be a swamp, because of which the city was not growing in a particular direction, but the city grew in a particular direction. Okay. So here what we have done is, first, you see, after this is very easy to analyze the growth. Second question is, based on the past growth, can we somehow do a prediction like in future where the growth will occur? Okay. In future, where will be the growth area? Can we do a type of a future simulation based on the past data sets? That is the second thing we have tried to do, but we have done all the things in a GIS environment. So you see, this is Dehradun area, Dehradun Valley. So what we have done is, first, you see, this is a land use. So here remote sensing has provided the spatial data. So here first we have generated a base map. What you see in red is the urban area. What you see in pink is basic the built up area which is outside the municipal area. This is the forest and this is the agriculture area. Okay. Then using a neural network we have trained it. You see, what we have done is we have generated these maps for the past few years. Neural network is a machine learning algorithm which, based on the past growth, it has learned how the city is growing. And once it has learned how the city is growing, then we have asked that network to predict how the city will grow in the future. So this is how we are using machine learning algorithm also for predicting the future growth in a GIS environment. Okay. Now see, the third thing is, see, we are you see, remote sensing, what we have seen is it can be used for generation of base map. We can do a temporal study how the city has grown. Then using machine learning algorithm we can also predict how the city will grow in the future. After that we can generate a base map to analyze the socio-economic data sets, like how the population is distributed based on economic, and whether which areas have got a better infrastructure, which have got a formal, which have got an informal development. Thirdly, we can assess also like what will happen if earthquake occurs in our study area, how many people will be affected, how many buildings will be damaged. This kind of things we have done. But one most important thing is the municipal authorities, they require latest maps so that they can earn for property taxation. You see, the municipal main source of resource or revenue for urban planning, urban local authority is basically the tax which is collected. So here what we have tried to do is we have taken a study area like this, and then this was Calcutta, part of Calcutta only, okay, and then we have generated a land use land cover map like this. So this exactly tells us how much area is built up, what kind of activity is going on, and how much tax that should be collected from each building. So you get an idea like how much money or how much revenue the building municipality should get from each area. If it is coming, okay. If it is not coming, that means we require to further do something so that we can increase our revenue database. Okay, so here what we have found out like is, see, what we have tried to map is how many buildings are occupied by the people themselves, how many are on rental, how many are government land. You see, most of the properties here are owned by the people themselves. Some are given for rental while some lands are for government. Okay, so you see what we have identified is 66 plots we have identified as not used by the owners. So these plots are registered as self, but actual the plots are for rental. So if a property is for rental, that means it should also give more tax. So this kind of analysis we can do by integrating the socio-economic data along with the spatial data in a GIS environment. So this tells us basically what is the family size. You see, how many buildings are having a single family accommodation, how many are having from 2 to 6 family accommodation, more than 6 government land. So you see, most of the here are basically single family accommodations, but are some are having 2 to 6 family also, and some are having more than 6 also here also, right? Now this tells us what is the tax zonation map of this. So it tells us the cumulative revenue that is generated from each parcel based on the revenue record. So this gives the idea how much revenue we are getting from each record, and this is one of the most important source of information for any municipality, because it is a source of income for the revenue of the municipality comes from this, and subsequently this money is only used by the municipality for providing us facilities like cleaning of the roads, lights also, sometimes drinking water also. This money is only invested by the municipal authorities for the development of various schemes in the city. Okay. Now this map tells us, this is a very important map. It tells us how much money is it coming expected. Secondly, it tells us how many people are paying the taxes and how many have not paid the taxes. So here we can identify which are the defaulters and how much money is evaded under the 79 plots. Here we identified some number of plots which were evading the tax. You see, so the municipality now knows how many people are not paying the taxes, what is the kind of activity that is going on inside this, how much families residing here also. You see, okay. So based on rental, rent use, family, we know how much tax is coming, but at the same time we can identify how many structures, how many buildings that are supposed to pay the tax are not paying, and how much loss of revenue the municipality has done. You see, this kind of activities are very important basically for the urban planning area, where you see regular monitoring and this is required. So this is not all the possible uses. We have got multiple uses where remote sensing and GIS can be used for urban planning. It can also be used for environmental studies. It can be used for urban land surface temperature studies, then power, then this environment, pollution. Number of scopes are there, but I have just tried to explain in brief some of the uses that the remote sensing and GIS applications can be used in the field of urban planning, but these are not limited to this only. We have got number of these things. So if you go across various papers published in various journals, you will come to know. But please remember, in this all, basically remote sensing serves as a spatial data provider, and GIS basically provides you an environment where you can handle these databases, analyze, and basically share it with the rest of the users also. So this is more or less from my side. Thank you very much for your attention, and now we, if any doubts and queries are there, then we can have some